Sorry. चलो.
Live.
Hello students. So today's class is going to be about adsorption and catalysis. Mostly we'll be dealing with adsorption and isotopes and the initial part of the chapter, more theoretical today. And all this comes under the chapter surface chemistry, as you're already aware. And today's session will be more theoretical and less of problem solving, because in the next session, say, we'll be handling more problems, and we'll be focusing more on JEE. And before we start off with that, we need to start with the theory part. Okay? So we'll start off now. So what we're going to do now is understand the basics of surface chemistry and see how things work, because as always, as they say, for JEE problems, the main important thing is to understand the basics, the fundamentals, and apply that in a higher level of critical reasoning. So high level of critical reasoning is something which you usually get over time with practice, or when you research more, when you handle the subject much better. But right now, so let's go on with the basics. Yeah. Surface chemistry. Hope my handwriting is legible to you guys. Let's see. So today's main topics that we're going to cover is what happens in the surface phenomenon, what are the different surface phenomena, and what is absorption, what is adsorption, and different types of adsorption, which is physisorption and chemisorption. And we're also going to check out what an isotope is, generally Freundlich isotope. And what else is left would be the same Freundlich isotherm in solution phase. So these are the topics which we're going to be covering today. So I want to take a note, because next time we have the class, I want you to be aware of where we stand, so that there will not be discontinuity. Yeah. Alright, so these are the topics. I advise you to take a look at it again. This is where we're going to be today. Catalysis, mostly we won't have time because we just have like 1 hour today. But like for covering these, and after that we'll cover catalysis in the next class, and after that we'll do some problems. Yeah. Right now we're going to start off with surface phenomena. So what are surface phenomena? So when you have, let's just say that I'm going to start with a hypothetical situation. When you have, let's say, an ocean, just like that, it's just there. There's a lot of water, and then there's the air. This is air, and the air has its own water vapor, breeze, winds, and all that. So if you notice carefully, there's different phases at work here. So you have a liquid phase, which is obviously the water, but by itself it has a lot of dissolved salts and all that inside it, and that is coming in touch with air, which is a gaseous phase. So here we have a liquid system, here we have a gaseous system, and again in the gaseous system, which is air, we have a lot of small particles which are suspended in air. So there's gaseous water vapor, there's solid particles like dirt and all that stuff. So it's a mixture, it's a different mixture, it's a heterogeneous mixture, which is here and it's here. So if you actually notice carefully, whenever the waves move forward, up and down, naturally the water sometimes gets a hold of some of the air and some of the particles which are present in the air. So these things get moved in, sometimes they become bubbles, they get absorbed into the water. And this is what you sometimes find as the salt oxygen, dissolved carbon dioxide, these kind of terms you'll notice. So these are two different phases, but they are coming in touch. And this is a heterogeneous phases. Similarly, let's just say this in air by itself has different phases. So there's a solid and there's gas. Solids are the dirt and all that stuff, and gases are and like you're aware of that. Similarly, same thing can be applied here also, where you have dissolved gas. So it's in a dissolved state, aqueous state. You have liquid and you also have solids. So when you have these different things, there's going to be two very significant or very important processes, phenomena which are going to be happening, and those are, one is absorption and two is adsorption. So just similar to this situation, hypothetical situation, let's just say there's a rock here. Let's just say there's something here, some solid, some kind of sponge. So there are different solids here and there. There's gas, there's liquid, all these things. So there's different mixtures all together, but they coexist in equilibrium. So they're all constantly undergoing changes here and there, but they keep retaining equilibrium. So among that, these two processes happen. What is absorption and what is adsorption? So absorption is basically when a uniform distribution of a certain material or molecular this thing over a complete the totality of a medium. For example, if I have, let's say, a sponge, and if I am going to pass some water through it. So when I pass sponge through water, and what happens is that the sponge absorbs water. So what happens here is that the water does not just go in and stay at one point. It goes through the sponge, throughout the sponge. This is something very similar you can notice with the tissue paper also. When you have a tissue paper, and the moment you put it on paper on water, you can see that it keeps passing, spreading, and then it becomes fully wet. So these cases where there is there's uniform distribution of a molecular species, is called absorption. So you can apply this to a lot of different these things. So when air gets absorbed by water, it means that if in case it does absorb, the air, whatever concentration or whatever amount of molecules were taken in, will uniformly be distributed across the body of water. So this is the idea of absorption. And adsorption, on the other hand, this is more like a surface phenomenon. A surface phenomena. So what happens in adsorption is it's a accumulation. Note this word. This is like basically understanding the concept. So this is what they're saying: accumulation of molecular particles or molecular species. You can use different words on the surface of a medium. This is adsorption. So for example, I have a metal block with me. Okay. This metal block, what happens is that it is surrounded by air. It's surrounded by air. But what happens is that due to atmospheric pressure or winds, temperature changes, what happens is that this gas gets concentrated at certain portions of the metal. So as you can see, this is the accumulation that I'm talking about. Accumulation of molecular species like air particles, which happens somewhere at different parts of the metal. So this is adsorption. So this is the difference. In case that it is absorption, wherein we have something like another similar metal block, where again, let's just say we have a similar condition of a fluid or molecular particles like air, then what happens is that in case of absorption, this will move in, but it will get absorbed evenly. It will get moved around evenly. there'll be evenness in the whole thing, compared to adsorption where it's only on the surface. So this is where adsorption makes a difference. It's very important for you to understand that it only happens on the surface. So why are we studying about all this is also another question. But what happens is that this difference of these two different things, so they play a major role in a lot of different processes. For example, absorption and adsorption form basis of a lot of different processes like electrodes, electrolytic cells. Electrolytic cell is one, as chromatography, and there's crystallization. A lot of different processes. So all of them are very important industrial processes. You see them being used a lot all around the world, and these different things, so the science behind them or the chemistry and the physics behind them is directly related to these processes like absorption and adsorption. So this is why we are basically going into surface chemistry and all that, because we cannot just define this with the rest of chemistry. This is another part of chemistry where just because it happens on the surface, as you can see here, it has a change. It changes the way things are. It changes the way the system behaves. It gives us results. So to explain that is the role of surface chemistry. So now we're going to go more into adsorption and look at the two types of adsorption. This color might be a bit bright, but like, yeah, let me try. Adsorption, it has two types. One is that it has, before we go to types, I think I should explain a bit more about adsorption because I think it's required. Adsorption, generally we define it for solids, where in solids like metals and all that, so you have this surface where it's an accumulation of particles, which we notice, and it need not be as straightforward as this. It could be like this, like different small particles like crystals, or could be anything. These things also have their own surface phenomena, and these are all regulated by different physical conditions like temperature and pressure. So these blue parts, as you can see, are the gases which are absorbed on the surface of the metals. So normally, if you think about it, these metals exist, so they're there in the system. Let's just say I have a box, these things there, and I have these gas molecules all around here. So adsorption is where these things which already exert a pressure, plus there's atmospheric pressure, right? This is a system. What happens is that these pressures contribute to something interesting, where these things go and attune to the top of those particles. So this is basically what adsorption is, and thermodynamics part of this is again like a very important thing. What happens is that this is the standard equation for Gibbs free energy, which tells us if it's spontaneous or not. And here, if you take this case, so there's already some gas molecules, but because of adsorption, they are able to attach themselves to the metal particles. So basically, the randomness or the number of gas particles which are around is lesser now. So they were all around the place. They were very random. They were moving here and there. But now, because of adsorption, they've stopped moving, or they've got stuck to the surface of the metals. So what does this mean? Is that S, which is entropy, has reduced. So entropy has reduced here. It's negative, which means this entity, this whole thing, is actually positive. There's a negative in front, so since this is negative, because reduction, this one thing is negative, multiplied by temperature, which is most like, yeah, temperature in all theoretical conditions is a positive number. So you have temperature into entropy as a positive number. Similarly, adsorption by itself is a spontaneous process. So spontaneity, it just happens, like just like in this case where they were just all around, just because of the pressure and temperature conditions, it already happens, which means delta G is negative. and this is why it's spontaneous. And let me write it here again, spontaneous. So here we have delta H, which is the enthalpy change. Delta H is very high, not very high, it's high for initial start, the starting stages of any adsorption. Delta H is a very high negative value. So as you can see, this thing is negative and this whole thing is positive. So if delta G has to be spontaneous, it has to be negative, which means delta H needs to be higher magnitude than this whole term. So this is where the math comes in, wherein at the start of any adsorption process, delta H is found to be pretty high. So what happens is that delta H has a very high value and it's exothermic. So adsorption, in all adsorption processes, the process is exothermic. When the molecules of gas or liquid, they get attuned to another different medium, the whole process is exothermic. It releases heat. Because of this, delta H is negative. It's negative and it's high in value. And here you have a positive value, T delta S entropy, which is obviously is still a significant number, but again, as initially at initial stages, this is the case, and delta G is highly negative at this stage, so it happens spontaneously. But after some time, what happens is delta H over time it reduces. So what happens is that delta H's magnitude over time, as adsorption keeps happening, is that the surface gets saturated more and more, and the reaction by itself is not happening as much as it did before. So what's happening is delta H is gradually reducing. So over time, with time, what happens is this delta H value gets lesser and lesser. At one point, it keeps lesser and lesser until one point may delta H becomes equal to T delta S. Basically, this whole thing becomes zero. At what point? After some time. After some time, this thing becomes equal to T delta S, and therefore what happens is that the value of delta G becomes zero. So at this stage is when adsorption, the whole system, goes into a stage of equilibrium. When delta G equal to 0 and when the enthalpy required is equivalent to the product of temperature and entropy change, we get equilibrium. So this is the equilibrium stage which we observe, because at normal conditions, when normally a system happens, entropy is reduced and then adsorption happens. So in a normal system like this, which we can observe, or in a lab where you can have different particles stored here and there, probably in a lab. So when adsorption happens in these cases, they already had all the time to reach a state of equilibrium. So they will already be in a state of equilibrium. Now, which means that these particles will already be adsorbed to some extent. Adsorbed. So now comes the second part, where the opposite of adsorption, which is desorption. So we already know for a fact that these things are already adsorbed some amount of gases or something into them. Now what we do is that we heat it. When we heat, what happens is that this heat plays the reverse role and it breaks the bonds or whatever relations it had between the gas molecules and the metal surface, which results in desorption. The adsorbed molecules are removed. The removal of adsorbed molecules is termed as desorption. So we just learned how thermodynamics works and why adsorption and desorption happen. Now we'll just quickly move to the next part, which is types of adsorption. So adsorption by itself, you should be asking this question as to why in the first place that I have a metal, there's gas particles here and there. Why are they going and or like what is the nature of the bond that they form, or do they form a bond in the first place? Why are they able to stick together with the metal and not just come out? So this is where we have something intermolecular attractions, like atomic level, molecular levels, where there's two types of adsorption depending on this. One is physisorption, and the second is chemisorption. So what is the difference between physisorption and chemisorption? Physisorption, as the name suggests, it's just a basic level interaction between these two molecules, wherein it is completely done by van der Waals forces. The nature of interaction between these two particles are because of van der Waals force. So this is in the case of physisorption. In the case of chemisorption, I think it's better that we do one at a time. So let's do physisorption first. Physisorption, what happens is that you have weak van der Waals forces which are bonding or binding the trapped gas molecules onto the metal surface. So this is why when you have the surface, when you have interactions, these interactions are slightly weak. It happens at the exothermic. The enthalpy is happens at 20 to 40 joules per mole, very low values, and that's very low level of enthalpy because all they need to form is just a van der Waals forces, so it has very low value. And what happens in this case is that there is no chemical bond, so they are slightly weaker, and desorption is much easier in this case. And if you talk about similarly in chemisorption has chemical bond is formed. I'm not going to explain much about chemisorption right now, but like I'm just giving you the side part. And in physisorption, it does not matter which gas is present because they will all be given almost similar partiality or preference towards adsorption. So for example, I have a metal surface here and I have multiple gases like CO2, CO, O2, N2, all these gases. So in this case, which one will actually adsorb more, or which one will adsorb first? So for this, there is one small technicality, which is the critical temperature. The higher the critical temperature, the more they get adsorbed, which means that if CO2 has the highest critical temperature, then it will be given more preference in forming and absorbing physisorption bond. Similarly, if O2 has the least value of critical temperature, let's just say this is 400 Kelvin or like any value, and if its O2 is the least critical temperature, it will be given the least adsorption. So this thing is driven by critical temperature, and it is only a physical change. As much as we think it is not, it is just a van der Waals forces. Doesn't take much time, and this process is reversible. Reversible as in there always exists an equilibrium between the system and the surrounding. For example, I have a system here. This is system again, the metal, surface, and the different gases. What happens is that there is an equilibrium of the number of particles or number of molecules of gases which get bound to the metal, and at the same time number of particles which keep released from the physisorption bonds. So this is what happens. It's in reversible and is usually at equilibrium. Yeah, and this increases, physisorption increases with increasing temperature and increasing surface area. So it increases with increased surface area, it increases. So I'm going to write it again. Surface area is proportional to physisorption. So the more the surface area, the more physisorption. The bigger the more surface area, the more adsorption is possible. This is slightly intuitive if you think about it, because the more surface available at the same conditions, it is possible for more particles to bind in. Yeah, and also this one has a very low enthalpy, as I told you. And one more thing is that in physics option, it's a very diverse process, as more to say dynamic process. Why? Because these different molecules which try to bond, so they form a multi-molecular or multi-layered structure. For example, if I have a metal here, it is not necessary that it needs to have like randomized these things, patterns. It can have different layers of adsorbed gases. How this happens is somewhat intuitive, like at one by one. So they can have different layers of adsorbed molecules, multi-layered. And if you just walk around to chemisoption is slightly a bit more into chemical changes and all that, because in chemisoption a chemical bond is formed. So if I have a metal here, and it's a case of chemisoption, there are bonds which are formed with the gas molecules, and this means that it's a chemical change. It's not reversible, correct? And it has a high enthalpy value required because of the formation of chemical bonds. It's not van der Waals weak forces, yeah. And also it is very specific, unlike the case where we had any number of gases which could be there, which I think is non-specific. Here it is specific, because whatever gas which is adsorbed, let's say O2 or N2, so only that gas is allowed to form bonds, and once that forms the bond with the metal surface, there is no going back. It's irreversible. So there is not going to be another layer coming in and all that. Since there's a physical process and there's a chemical process, so that is where the difference is. So that slot is taken over by another molecule, that is done. Yeah, so it's very specific, and because of this, it is mostly unimolecular, because there's only one type of bonds which are formed. And again, in this case also, there's a direct connection between surface area and adsorption. So mainly these are the conditions. So pretty much chemisoption, it's a chemical bond. In physics option, it's van der Waals forces. It has low enthalpy and it can easily be reversed, and it is not at all specific. In this case, it's irreversible and has high enthalpy because of the formation of a chemical bond, and is usually unimolecular and is very specific. And again, something which is similar to both cases of adsorption is the only one point, which is that surface area is proportional to adsorption. So this is what we need to learn about physics option and chemistry option. Mostly in cases where they ask you questions about the nature of adsorption, you just have to think about it. Key, is there a certain condition given in the question that it is a physical change or a chemical change? That is all that you need to check, and using that there will be a lot of theoretical questions which comes up, wherein they'll ask you if they'll give you an equation which is reversible initially, but then they'll be like, at certain condition it becomes irreversible. So what is the difference? What happened now? Like how does the enthalpy change? All this time. So it depends. For some cases it's physics option, some cases chemistry option. They might try to give you questions where both are possibly coexisting, and hypothetical systems where you'll have to answer according to that. It's intuitional. Yeah. So that is all about chemistry option and physics option. Now we'll go to something very interesting and probably the most important part of this chapter, which is Freundlich isotherm. Freundlich isotherm, was discovered by Mr. Froelich, the scientist's name. What it tries to tell us is that it tries to give us an equation using which we can explain how much of adsorption is possible at different conditions of temperature and pressure. So he's given an equation which is pretty much the core of this whole concept, and I'm going to go ahead and write it now. So it's x by m is equal to k p powered 1 by n, where n is greater than 1. So in this case, k, p and n are all constants. Whereas x is mass of adsorbent and m is mass of adsorbate. Sorry, I said it the other way. This is mass of adsorbate. And this one is mass of adsorbent. You can remember this similar to solute and solvent, wherein it ends with TE and ends with ENT. Something similar to solvent and something similar to solute. Very similar, just keep it in mind. So this is the Froelich isotherm equation. So what it says is that the rate of adsorption for mass of adsorbate, which is adsorbed into the mass of adsorbent, is equal to k p power 1 by n, where k, p and n are all constants. So p is not like it's pressure, not pressure. That's not the case. It's a constant in this case. Okay. So what happens is that when you use this equation and at different temperatures, when you plot, as you can see, it's a equation which can be plotted, and what happens is people get a relation like this. So you see that at different temperatures, and this one is something which was given to us in the text. I'm going to use that only, and as you can see, it's a direct plot between x by m and p. So this is the graph, as you can see, for Froelich isotherm, which is done for a certain gas at different temperatures. So as you can see, they all have this variation. This as the temperature keeps decreasing, the graphs keep going higher. The rate of x by m by p is increasing, and this doesn't give us much results, which is why they convert Froelich isotherm's main equation into an auxiliary equation by applying log. So why they're using log is because we can have more linear quadratic equations max to max to solve our problems, compared to this, which is going to go into exponential 1 by n and all that, p, k. So if you have a complex scientific equation with 1 by n with e and all that, it's going to get pretty complex. So what we're doing is that we're going to apply log to this equation right here. So if you apply log on both sides, you get log x by m is equal to 1 log of k, first term, plus, since it's a product, it's log, you get log of p, and since 1 by n is in power, it will come before that. So this is the main equation which is normally used in the Froelich isotherm. So in this case, if you use this equation, and now if you try to form a graph, you can see that this is in the form of y equal to mx plus c. So this is y, this is c, its k is a constant, and this is mx. So m, as you know, is the slope, correct? And in this case, that is 1 by n, and x is log p, y is log of x by m, and c is log k. So now the graph becomes much easier, much more convenient, wherein you get a straight line. It's an equation of a straight line, unlike this, which is exponential. The straight line equation. So if this is our equation for a certain isotherm, now what happens is that if you bring it back here, this is the intercept, and this intercept will be c. Remember, geometry vector. So this happens to be log of k, and the x-axis, as you can see, happens to be log p, and the y, as you can see, becomes log of x by m. So as you can see, x by m, theoretically we can find that value pretty much easily, because this is the standard values which we get, x by m. So we can just take log and plot it on one side, and p, which is another constant which we can find it here, and then we find the slope. So this is our x and this is our y. The slope value you get from here, and this is our c. This is the equation. So this equation gives us more data. It lets us understand things much better, and this can be applied to different systems and gives us more clarity. Yeah. If you remember what Freundlich isotherm is, again, let me say it again, is that you have an adsorbent and an adsorbate system where adsorbate is getting adsorbed into the adsorbent. In that case, the rate of adsorption, like mass ratio, will be equal to a product of different constants. Yeah? Now just imagine hypothetically that if n or 1 by n is given to be the value of 0. Let's just say in a certain value this 1 by n becomes 0 and 1 by n is 1. So 1 by n can only be a value between 0 and 1. Yeah, it cannot go over than that, because n is greater than 1. It can always, it's a fraction between 0 and 1. So 1 by n, which is between 0 and 1. So in this case, what happens? So these are different cases for 1 by n, where we know that n is a constant. Is that if 1 by n is 0, you get, in this equation I'm substituting it here, so you get x by m is equal to k into p power 0. So p power 0 will become 1. I'm just going to write it like this. X by m is equal to k. It's a constant, so the rate of absorption here becomes a constant. P, as we know, the pressure. So now what happens is, if the same exact thing here, this equation will be the same as this equation, general equation, and last but not least, 1 by n is equal to 1. So the maximum value it can attain, the 1 by n value. Now you get x by m is equal to k into p, or I can say x by m is proportional to p, the pressure. So now what happens is that your pressure is directly proportional to the adsorption. Sorry. So the more you increase the pressure, the more adsorption happens, and the lesser the pressure is, the lesser it happens. It becomes a directly proportional equation here, only given in the case of n equal to 1. But what happens normally is this value in reality, or like normal cases, is between 0.1 to 0.5 normally, which makes it like the normal values. So we generally don't see these two cases, but yeah, there are theoretically cases which can be applied. And just like Freundlich isotherm, where you're talking about solid and then all that, which is taking it from a gaseous state. Now we're going to look at a case of Freundlich isotherm where you have a solution. You have a solution, but what I'm doing is I'm going to throw, or I'm going to place a solid, the adsorbent, this adsorbent. So previously in Freundlich isotherm, the case was we had placed the metal or the adsorbent in open air or free air. So that time it was a gas getting adsorbed into a solid previously, but now we are doing it the other way. This liquid which is getting adsorbed into a solid adsorbent. So what will be the difference? Can we find a relation for this which is similar or equivalent to Freundlich isotherm? Freundlich isotherm in this case slightly changes into a bit more technical equation, wherein the equation is dependent on the concentration. So in the previous case, as we saw before, we saw x by m was equal to k into p power 1 by n, and we know that p is the pressure that time. This is for Freundlich. So same thing for solution phase, Freundlich part 2, the solution phase. What happens is the equation, instead of pressure which was applied for gases, we apply something else, which is concentration. The equation changes into this, where x by m is equal to kc power 1 by n, where c is concentration of the solution. So this changes things. Because now the equation has slightly changed because of the introduction of concentration instead of pressure. And now the equation will also tell us one thing, that it is proportional. The absorption rate will now be proportional to concentration, and it will also depend on nature of adsorption and adsorbent. So it depends on nature of adsorbent as well as concentration. Otherwise the equation is pretty much similar to what we learnt in Freundlich system. So this equation is important because I'll tell you how it works in JEE problems. So normally in the questions which they give, they will define the phases which are provided in the problem. For example, there's a metal surface and you have a gas, then you go for Freundlich isotherm. And similarly, if there's a liquid, you apply the solution phase formula of the same thing. There could be interrelated problems as well with multi-systems where there's two of them getting adsorbed. One is from a solution and one is from the air. Something like this, where you have a solution and there's a metal which is like this. So they could ask you like, what is the rate, what is happening here? So in this case you will have two different cases of adsorption happening, one here and two here. So you will have to correlate. Yeah. So keep this in mind, the second equation. Last part of today's discussion before we are running out of time are the applications of adsorption. So this is pretty much a straightforward this thing. It's a more theoretical thing, like what do we use adsorption for? So adsorption by itself, what it does, we know, is that it separates a certain gas or a lot of gases from an existing phase. So if there's a metal and there's an adsorption happening, it takes away certain particles, and we already know for chemisorption it's very specific. So if we can identify chemisorption for different phases and different gases, different solids, we can actually identify and remove certain very specific gases. So this is the main concept principle behind it. So the main uses that are there are one of the main uses, which is chromatography, and there's vacuum, creating a vacuum. So and there's flotation, curing diseases. So these are a lot of, like if you check your text you will find at least 20-30 applications, but mainly like chromatography, you have different this thing to find out the nature or the concentration, to find it using a chromatography paper. And then there's finding a vacuum, where you already have a system with very few particles left. In that case you introduce a metal which will absorb whatever is left, and then because of the high pressure, Freundlich isotherm, the pressure is very high and therefore it will get absorbed, and therefore you get close to vacuum. For flotation, the ore mixture, in that they introduce again an adsorbent in order to remove the certain very specific gain you from that. And curing disease, so this is a slightly new modern application where we can observe that certain chemicals or certain particles which are in the body can be removed or cleaned using very micro adsorbents. This is a slightly new one. You can Google it up. It's a pretty interesting topic to be learned about. So that's it for today, and mainly we are going to be seeing more about two topics after this. One is colloids, and second one is catalysis. And after that, we'll be solving problems. So until then, until the next class, I'll see you soon. Yeah.